Back. Some good news before we jump ahead. The last two lectures were by far the most complicated material in this class. So make sure you take the time to go back and take a look at them and try to review them as much as possible. But now we have that stuff behind us. So for this lecture, we're going to talk a little bit about how air is actually able to get pushed up into the atmosphere. Because everything we've talked about so far has to do with if we push air up into the atmosphere, it'll rise if the air is unstable, it'll sink if the air is stable. But what actually allows air to rise? Well, the good news here is you don't need to think about lapse rates or adiabatic this and that. You don't have to worry about any of that here. All you have to think about is the fact that there are actually four mechanisms in the atmosphere that allow air parcels to rise. If we didn't have these four mechanisms, air parcels would just hang out near the ground, and stability versus instability would be irrelevant. Just like the ball in the valley or the ball on the hill, nothing matters unless you push the ball. If you leave the ball alone, if you don't push it, if you don't displace it, nothing happens. It's once you displace it that the real fun begins. Well, how on earth does air get displaced from the surface of the earth? What is the kick? What is the nudge that makes this happen? Well, there are four mechanisms. I'm going to blitz through them right now, and then I'm going to talk about each one with a little bit of depth. The first is called convective lifting. The second mechanism is called topographic lifting. The third is called convergence. And the fourth is called frontal lifting. Now, let's jump in and talk about each one of these. So, here they are right here, all just taken from the textbook. And what you see is, in the case of convective lifting, you have air from the surface that just rises because it's been heated. In the case of topographic lifting, air is pushed along a mountain, forced to rise up and over the mountain. In the case of convergence, you have air coming from all sides converging at one location, and that forces it to rise. And then finally, along fronts represent a boundary between warm air and cold air. The warm air is always forced up and over the cold air. And so each and every one of these processes pushes air up into the atmosphere, where it then cools, condenses, and forms clouds. This is why rising air is so important, because without it, we don't have clouds. These four mechanisms are the kick. They are that nudge. They are the displacement. They are what get air from the surface of the earth up into the atmosphere. And then the stability of the atmosphere then determines if the air can continue to rise or if it just sinks right back down. So let's talk about each one of these in a little bit of depth. First, let's talk about convection, this is really review. Convection is a heat transfer, and it happens when the surface of the earth gets heated by the sun. The very, very, very bottom layer of the earth heats up due to conduction, and then this creates a layer of air that is much warmer than its surroundings. It then rises up, cools and condenses, and we get cloud formation. Now, convection is the kind of rising air that creates cumulus and cumulonimbus clouds. And in fact, during the summertime, there's a lot of convection present in the atmosphere here in the United States, especially on the eastern end of the Rocky Mountains. And so there's a lot of thunderstorms. So convection, again, looks something like this. Air from the surface rises. As it rises, it expands and it cools. That creates condensation. We get a cloud that forms. and then cold air is displaced, pushed downward where it sinks, warms up, and then rises. And so we get this convection current. Again, that's primarily review. Now, if you've ever lived here in the Bay Area, and I assume if you're taking this class that you live here in the Bay Area, you've probably seen a lot of times where clouds are present up on the mountains. Maybe not down here near the base of the valley, but up on the mountains, we can see clouds. The reason why is because of what's called orographic lift. Oro means mountain, graphic uplift means up and over. So orographic lift means air that's pushed along a mountain and then up and over the mountain. So in this case, here on the front of the mountain, this is what's called the windward side of the mountain. Wind is blowing towards the mountain. Once it reaches the mountain, it can't go through the mountain. It has to go up and over the mountain. As it goes up, those parcels of air expand, cool, and condense. If the air up here is unstable, that air can continue to rise. If it is stable, then it'll just sink back down the other side. But this creates a lot of clouds on the windward side of mountains. This also produces a pretty interesting effect called the rain shadow effect. And this is actually why San Jose doesn't really get a lot of rain. It's because air that's pushed up and over the Santa Cruz Mountains condenses on the windward side. It condenses on the windward side. As a result, by the time it comes down the other side of the mountain, called the leeward side, it's much drier air. Now this is important because this creates a situation where the air on the windward side near Santa Cruz is very moist. Therefore, there's a lot of clouds and a lot of rainfall. On the other hand, once that air gets up and over the mountain and down here towards San Jose, it's dried out and it actually becomes very hot. This also occurs because as air rises up the mountain, it actually cools moist adiabatically because the parcels in the air are saturated. However, once it reaches the other end of the mountain, those parcels have lost most of their moisture. The moisture's rained out, it's formed clouds, it's rained out. Therefore, the parcels are much drier, and therefore, as they come down and sink down the other side of the mountain, they actually warm up dry adiabatically. So they warm up faster than they were cooling. As a result, they become substantially warmer on the leeward side of the mountain. This creates winds that are actually hot and dry. So the process looks something like this. So let's say over here is Santa Cruz, and you have moisture over here because you're right near the ocean, and you have parcels of air over here. As these parcels of air are pushed up the Santa Cruz Mountains, they quickly become saturated and they quickly condense, forming clouds. Once this air rises up and over the Santa Cruz Mountains, moisture is condensing and escaping the parcel. That's making the parcel drier and drier and drier. Eventually it makes it to the other side of the mountain where it sinks, and as it's sinking, it actually warms dry adiabatically. So it becomes a much warmer air parcel by the time it reaches the surface. It's much warmer and much drier. As a result, the air here on the leeward side is much warmer and drier. That's why if you live in Santa Cruz, it can be very mild and moist in the summertime, whereas here in San Jose, it could be very hot and dry. And this is just a good example, a good comparison between the two. In Santa Cruz, the average annual rainfall is almost 31 inches of rain. Whereas here in San Jose, the average rainfall is closer to 15 inches. So only half as much as Santa Cruz. The air temperature here is also much warmer than Santa Cruz. And it's because of this rain shadow effect. Pretty cool when you think about it. Like, that is why it's so much drier here in San Jose than it is over in Santa Cruz. Now, the next type of cloud development is called convergence. Have you ever had one of those moments in your life when you felt like you were a magnet and everything was coming towards you? Everything was coming towards you. Let's say you were at a birthday party and it was your birthday party and 8 people all at once want to come to you and wish you happy birthday. And you see all these people getting closer and closer to you. Well, those people are converging on you. Well, convergence also happens in the atmosphere. And what actually happens is air gathers at one location from many different places. It comes in from many different directions and it converges at one singular point. Once it converges, it does the good old heave-ho where it rises, it expands, and it cools. This actually creates low pressure at the surface of the Earth. Now we'll talk more about that in the next module, when we talk about high pressure and low pressure. But for now, all you need to know is that winds are converging at one location. All these winds are colliding at one location, and at that location, the air is being forced up. Then it cools and condenses. So it looks something like this. You have air coming from different locations, so air coming from here, air coming from here, air coming from here, and so on. It all converges in this area of low pressure that then rises up. Now, I'm not sure what your background is on meteorology, but when I was a kid, I was fascinated with this stuff. And one of the things I always wondered was, why low pressure? Why is it that rain forms around low pressure, but never high pressure? Well, this is it. Right here, because around low pressure, you have a lot of rising air. Now, just a quick spoiler alert for the next module. In that module, we'll be talking about high pressure where the air is sinking. And therefore, there's no clouds there. The last type of lifting has to do with fronts. And in a few modules, we'll actually cover fronts more in depth. With that said, along the front, you have a warm air mass being pushed up and over a cold air mass. When that happens, it does what I hope you all now have committed to memory. It rises, expands, cools, and condenses. Remember that. Next midterm's coming up soon, and you want to make sure that you have that in mind, because I guarantee you'll see something on the midterm about that. Rises, expands, cools, and condenses. Now, cold fronts are much sharper than warm fronts. Along cold fronts, that warm air is pushed straight up. And so you get tremendous amounts of convection, tremendous amounts of thunderstorms present along cold fronts. On the other hand, along warm fronts, that warm air rises at a much more gentle angle, and therefore the clouds are usually much more spread out. It looks something like this. When you have this warm air, it rides up and over a cold air mass. In the case of a cold front, like this one over here, it's forced almost straight up. As a result, it shoots straight up, and that's what gives us thunderstorms. On the other hand, here along a warm fronts involve much more gently rising parcels. As a result, the air is typically a lot more spread out. The clouds are typically a lot more spread out. Now, that's it for this topic. So, in this topic, we just quickly went over the different forms of cloud formation. Just to review, they are convection, topographic lifting, which also gives us rain shadows, convergence along a low pressure system, and frontal lifting. Now, for the next 2 lectures, for the rest of this module, we're done talking about rising parcels of air. For the next 2 lectures, we're going to be talking about precipitation. That's that stuff that falls from the sky. Until then, I'm Terrence Mullins. Thank you for watching.